Hey guys, welcome to my YouTube teaching learning platform. Today we are going to start a new unit which is phase equilibrium. So in this unit, first of all we'll discuss about phase, component and degree of freedom or variance. Then we'll see the phase rule and how this phase rule is derived, and at the end we will solve some numerical problems based on the phase rule. So without any further delay, let us start today's class. Basically the phase equilibria is used to study the system existing in heterogeneous equilibria. During the study of chemical systems, we usually deal with the system containing two or more phases in equilibrium, which are called heterogeneous or polyphase system. So in this phase equilibria, a generalized phase rule was derived, which is based on the basis of the principles of thermodynamics. The phase rule is able to predict qualitatively by means of diagram the effect of changing temperature, pressure or concentration on a heterogeneous system in equilibria. So in this unit we will study the phase rule and its various applications in the daily life. So before starting the unit, let us see some terms which are frequently used in phase equilibria. These are first one is phase, second one is component, and third one is the degree of freedom or variance. So we will discuss all these three terms in details one by one. So let us start with the first one, phase. A phase is defined as any homogeneous and physically distinct part of a system which is bounded by a surface and is mechanically separable from other parts of the system. For example, a gas mixture constitutes a single phase since all the constituent gases are completely miscible. Secondly, immiscible liquids constitute different phases. For example, carbon tetrachloride and water, which do not mix with each other, form two phases where both the phases are in the liquid state. Thirdly, completely miscible liquids such as water and alcohol and benzene and chloroform constitutes one phase system in which all are liquid because these liquids are mixes completely. Next one is an equilibrium system where calcium carbonate in solid state undergo decomposition to produce calcium oxide in solid state and carbon dioxide in gaseous state. Here there are two solid phases and one gaseous phase, so it is a three-phase system. In this figure you can see this is a mixture of immiscible liquids, ether and water. So ether and water, these two never mixes with one another, so we can see a distinct clear and distinct boundary between the two liquids which separates ether and water from one another. So this is an example of a two-phase system in which both the phases are in the liquid state. Now let us see what is component. The number of components of a system at equilibrium is defined as the smallest number of independently variable constituents by means of which the composition of each phase can be expressed either directly or in terms of chemical equations. For example, water exists in three phases: ice in the that means the solid state, liquid water and water vapor. However, the composition of each phase can be expressed in terms of water H2O. Hence, it is a one component system. Okay. Consider another example in which sulfur exists in four phases, that is rhombic sulfur, monoclinic sulfur, liquid and vapor sulfur. But since the composition of each phase can be expressed in terms of sulfur only, so it is a one component system. On the other hand, in a chemically reactive system, the number of components is given by the formula C is equal to N minus E, where n is the number of chemical species and E is the number of independent equations relating the concentrations of the n species. For example, when calcium oxide and carbon dioxide are formed by decomposition of calcium carbonate, the system can be represented by the equation this. So here there are three number of chemical species, that is calcium oxide, carbon dioxide and calcium carbonate. So n equal to 3 and the system can be represented by one equilibrium equation. So E is equal to 1. Therefore C is equal to n minus E, that means 3 minus 1 is, which is equal to 2. So this is a two component system, that means number of component in this system is equal to 2, right? Then next one is the degree of freedom or variance. So it is defined as the smallest number of independently variable factors such as temperature, pressure and concentration, which must be required in order to define the system completely. Degree of freedom of a system is also known as variance. So when a system having no degree of freedom, f is equal to 0, where f is the degree of freedom, and it is called non-variant system or invariant system. When a system having only one degree of freedom, that is f is equal to 1, it is called a univariant or monovariant system. Similarly, a system having 2 degrees of freedom is called a bivariant system, and so on. So basically degree of freedom means it is the number of independently variable factors, namely temperature, pressure and concentration, which must be specified in order to describe a system completely. Okay. Now let us see what is the phase rule. The phase rule is an important tool used for the quantitative treatment of systems in equilibrium. It was introduced by J.W. Gibbs in 1876 while investigating heterogeneous equilibria. According to the phase rule, for a system in complete internal equilibrium, the degree of freedom, the number of components and the number of phases are related to one another by the equation f is equal to c minus p plus 2, where f is the number of degrees of freedom, c is the number of components and p is the number of phases. So this phase rule is given by this equation, which is f is equal to c minus p plus 2, right? Now let us derive the phase rule. So phase rule is also known as the Gibbs phase rule, and it can be derived on the basis of thermodynamic principles as discussed here. To derive this, let us consider a heterogeneous system consisting of p number of phases and c number of components, in which C1, C2, C3 up to Cc number of components exist in P1, P2, P3 up to P number of phases. So let us assume that the system is non-reacting, that is the passage of component from one phase to another does not involve any chemical reaction. When the system is in the equilibrium state, it can be explained completely by specifying the following variables, that is temperature, pressure and composition of each phase. Now the degree of freedom f is given by the equation degree of freedom f is equal to total number of variables minus number of variables defined by the system being in equilibrium. Okay. Now total number of variables required for specifying the state of the system is temperature, which is same for all the phases, pressure, which is also same for all phases, and concentration. So independent concentration variables for one phase with respect to the C components is equal to C minus 1. Since the concentration since if we know the concentration of one component for a two component system, then the concentration of the other can be determined by difference. So concentration of any last component is independent. So therefore the independent concentration variables for one phase with respect to the C number of component is equal to C minus 1. Again, independent concentrations variables for P number of phases with respect to the C number of components is equal to P into C minus 1. So therefore the total number of variables is equal to P into C minus 1 plus 2, and this give it equation number 1. So this 2 arises due to the temperature and pressure, the two factors which are same for all the phases. Then we'll see what is the total number of equilibria equations. The various phases present in the system can remain in equilibrium only when the chemical potentials denoted by mu of each component is the same in each phases. So therefore mu1 p1 is equal to mu1 p2 is equal to mu1 p3 is equal to up to mu1 p, which are all equal for the component 1. So similarly mu2 p1 equal to mu2 p2 is equal to mu2 p3 up to mu2 p, which are also equal for component 2. And if we go on like this, then we will get mu c p1 equal to mu c p2 is equal to mu c p3 up to mu c p for the component C. So therefore for each component of the number of equilibria for P number of phases is equal to P minus 1. Since one independent equilibrium equation is required to describe two phases in component 1, and similarly two independent equations are required to describe a three number of phases in component 2. So if we go on like this, then we will find that for P number of phases the number of independent equilibrium equations required is equal to P minus 1. So for C component the number of equilibria for P phases is equal to P minus 1 multiplied by C. So therefore the total number of equilibria involved E is equal to C into P minus 1. Give it equation number 2. Now we have the degree of freedom F is equal to total number of variables minus number of variables defined by the system being in equilibrium. So therefore F is equal to P into C minus 1 plus 2, which is given by equation number 1, and it is the total number of variables, minus C into P minus 1 given by equation number 2, which is the number of variables defined by the system being in equilibrium. So this implies F is equal to Cp minus P plus 2 minus Cp plus C, and on simplification we get F is equal to C minus P plus 2. So this is the phase rule, or this equation is also known as Gibbs phase rule equation. Now let us see some conclusions obtained from the phase rule. First one, when the system consists of one phase and one component, we have C is equal to 1 and P is equal to 1. So according to the phase rule, we get F is equal to C minus P plus 2, which is equal to 1 minus 1 plus 2, and it is equal to 2. So the system has 2 degrees of freedom. Secondly, when the system consists of two phases in equilibrium and having one component, we get C is equal to 1 and P is equal to 2. So substituting the values in the phase rule equation, we get F is equal to C minus P plus 2 is equal to 1 minus 2 plus 2, which is equal to 1. So F is equal to 1. That means the system is monovariant. Now consider another case. Is it possible to have a one component 4-phase system? Let us check this. If C is equal to 1 and P is equal to 4, then F is equal to C minus P plus 2, which is equal to 1 minus 4 plus 2. So this implies F is equal to minus 1, and this is absurd because the value of F cannot be negative. So it is not possible to have a one component 4-phase system which can be proved mathematically, and in actual practice also it is not possible. So again, let us solve some problems. The problem is that we have to determine the number of degrees of freedom in all the following systems. First one is liquid water and water vapor in equilibrium, and second one is the decomposition of potassium chloride to produce potassium chloride and oxygen gas. So to solve this equation, in the first problem we have a one component system, because water, liquid water and liquid water vapor can be represented by only H2O, that is water. So number of components C is equal to 1, and number of phases P is equal to 2. Since there are two phases, one liquid phase which is liquid water and one vapor phase which is water vapor, so P is equal to 2. So substituting the values in the phase rule equation, F is equal to C minus P plus 2, we get F is equal to 1 minus 2 plus 2. This implies F is equal to 1. So that means only one variable, temperature or pressure, is needed to be specified to describe the system completely. Okay, and the system is monovariant. Now let us solve the second problem. Here in this problem, a equation in equilibrium is given where potassium trichloride KClO3 undergo decomposition to produce potassium chloride in solid state and oxygen in gaseous state. So here C is given by number of component C is equal to n minus E, which is equal to 3 minus 1, because here number of species involved is 3. One is KClO3, other one is KCl, and the third one is oxygen. So n equal to 3 minus E is equal to 1, because this system can be represented by only one equilibrium equation. So E is equal to 1. So therefore C is equal to 3 minus 1, which is equal to 2. Here the number of phases E is equal to 3. 2 in the solid phases, which are potassium trichloride KClO3 and potassium chloride, both are in solid state. So 2 solid phases and 1 gaseous phases, which is the oxygen gas. So therefore substituting the value of C and P in the phase rule equation, we get F is equal to C minus P plus 2, which is equal to 2 minus 3 plus 2. So this implies F is equal to 1. That means here also only one variable, temperature or pressure, is needed to be specified to describe the system completely. Okay, so these are very simple problems which can be easily solved. To solve this type of problem, just you have to specify what is the number of components and number of phases in the system. Okay, so all of you try to solve more problems, and if you face any difficult problem, then please share with me. You can also post your questions in the comment box. Together we will solve those type of problems. Okay, so thanks to all of you for your patience. See you in our next class. Till then, enjoy your learning and take care.